joy to be your host. I am Dr. Frank Summers of the Office of Public Outreach. And we have an amazing audience here for you tonight, Bonnie. Saturn really sells, okay? So we have a packed house here tonight. We may not have any more. We have a couple lithographs down here. We started out giving out the Monkey Head Nebula. We sold out of the Monkey Head. We had to go to the 30 Doradus, which is also known as the Tarantula Nebula. So if you didn't get monkeys, you got tarantulas, okay? And if you're afraid of spiders, well, I'm sorry, that's all we have left. Please come down and grab one if you didn't on the way in. Our talk, do I even need to say tonight, is, whoops, I got to turn this on. Our talk is Cassini's Grand Finale at Saturn. And we've been only waiting 19 years and 11 months for this because that's when Cassini launched 19 years and 11 months ago. Absolutely looking forward to it. It's a lot of fun. Upcoming next month, Elizabeth Tasker from the Japan Aerospace Exploration Agency. She'll be coming in and talking about dangerous worlds. Yes, exoplanets and such. All right. And you can see our familiar TBA coming in December and January, which means I was working on some stuff for the end of the fiscal year and didn't nag people to sign up for talks. Actually, I have one scheduled for January, but we may have to change that. I don't know, with the news. So, anyways.
It can still be on the 9th.
Yeah, okay.
As long as it's on the 9th, we can still
As long as it's on the 9th, great. We can do it on the 9th. Okay.
You'll get a tag team of people.
Okay. Ooh, tag team on the 9th. Okay. We still have some, there's a couple extra seats down here if the folks who are standing in the corner would like to. If you have a seat next to you, raise your hand so these guys don't have to stand for the whole night, okay? All right. Let's see, website. If you use your favorite search engine and look for Hubble Public Talks, you'll find this page with the list of the upcoming lectures, the links to watching it live online, as well as in the archive, and the boxes where you can subscribe or even unsubscribe to our mailing list and get the monthly reminders of the talks. And actually, also we send out the monthly listings of where it is on the webcasts. Okay. Announcements, yeah, sign up at the website or you just give me your email address. And if you have comments or questions, you can send them to publiclecture@stsci.edu. If you would like social media, we have Facebook, Twitter, YouTube, Instagram, and maybe a few more things that haven't listed here. I myself am on Facebook, Google+, and Twitter every now and then, and have a blog on Hubble site if you want to follow me. The observatory, yes, the weather appears to be permitting tonight. And Irini sent me a text and said, yes, she will be doing it. So we will be meeting at that door over there, okay? Now, unfortunately, and it's really hard to tell an audience of this size, she can only take 15 to 20 people over, okay? And I know there's like 200 of you here tonight. So if you have been before, please let somebody else who hasn't been. And if you don't get to go tonight, please come back and you will be able to do it after another lecture. Or you can go to md.spacegrant.org, find this web page, and they have open houses most every Friday evening, okay? They update this web page at like 6 p.m. or 5 or 6 p.m. on Friday to tell you whether or not it will be open, and you will get a longer observing session at their open house than you will get after the lecture here, okay? And as we're going into fall, we've just passed the equinox, the nights get longer, and so lots and lots of observing is possible, okay? All right, and now my part. News from the universe for October 2017. Unfortunately, the top story tonight is JWST launch delay. No, you got to do that all together. 1, 2, 3. Thank you, okay? So this is a drawing of the James Webb Space Telescope. It will be NASA's next great observatory. It is an infrared telescope with a 6.5 meter mirror, 18 segments. It will be launched and go out 1 million miles from Earth, so it is nice and cool and away from the influence of Earth. It'll have these great sun shields to also keep it cool. It will do amazing things. It will do things Hubble cannot do. But it won't do them on the time scale we had hoped it would do them, okay? It was slated to launch in October 2018. That is no longer the launch date. NASA had a press release last week, and I'm quoting from it. It says, is planning to launch between March and June of 2019. So it's about a 6-month slip in the schedule. It is not indicative of hardware or technical performance concerns. They want to make sure that, look, everything's going fine. We just want to make sure it's perfect because, unlike Hubble, we can't go out and service this, okay? So integration of the various spacecraft elements is taking longer than expected, all right? And they want to make sure they do it right. And one other thing in terms of the financials, the existing program budget accommodates the change in launch dates, so you as taxpayers are not going to pay extra for this delay. It's all within the program budget. They build a lot of contingencies into these plans, and unfortunately we've had to take one of those contingencies. So instead of October 2018, we're looking between March and June of 2019. It will be worth it though, okay? It really will. All right. Our second story, a tale of two comets. Yes, I didn't quite come up with a real Dickensian story to go here, but I just like the title. All right, so first of all, what we're talking about here is the asteroid belt, okay? This is the orbit of Jupiter out here, and in here in the center we have the orbits of Mercury, Venus, Earth, and Mars. In between where you see all these green things and the red things, those are the main belt asteroids. There are several 100,000 of these asteroids. However, also in that area are a lot of comets, a lot of short period comets. And we're going to talk about an object that is actually both. Here. So, in November 2006, they discovered an asteroid, and they called it 2006 VW139. That's the standard nomenclature that we give to asteroids when we discover them. And then they observed the same object in November 2011, and they found that it had a tail. And tails indicate that it's a comet. So they also gave it the designation of Comet 288P. All right, so it had both asteroid designations and a comet designation. Well, that's obviously an interesting object, so what are you going to do? You're going to take Hubble and you're going to look at it. And Hubble looked at it in August of 2016, and Hubble saw this. Ooh, what do we see? We see in the center not one, but two bright spots in the center. So as you can see, I've updated it to be a binary asteroid, 2006 WV139, and I guess you could call it a double nucleus comet, 288P. We have an object that appears to be two objects. Now, in examining it and trying to understand it, they estimate that it was a single object that broke apart about 5,000 years ago. And then the gases that are exposed caused jets, and then the two pieces moved away from each other, okay? That also produced material that streams out as this tail. So Hubble looked at it not just once, but 5 times. And we looked at it in September 1st, and September 9th, and September 20th, and September 29th. And what do we see? We see the tail wagging, okay? Yes, comets wag their tails, right? So here are those 5 images. But you can see they only occur over this time scale of about a month. Now, some of the change of the orientation of the tail is due to the different geometry of Earth and the comet, or asteroid, as it was. But over the course of a month, it wouldn't change that far. So what they really think is that it's also due to different types of particles being emitted. The larger particles are here. These are on order millimeter size. When I say large, we're talking tiny, tiny dust particles, okay? This is a dust tail. The tiny, tiny dust particles, about 1 millimeter. Those are large in astronomical terms here. 1 millimeter in size are blowing off in this direction due to how they're being ejected. But by this time, the dust was mostly very, very small, about 1/100th that size, or 10 microns. And those 10 micron particles get actually pushed back by the radiation pressure of the sun. And so here is where the tail is actually pointing away from the sun, like a normal comet dust tail does. And here it's not quite pointing away from the sun due to the larger particles in it. So we have a really cool object that's part asteroid, part comet, and is able to wag its own tail. Kind of cool. All right, our final story for you is candles in the dark. Now, candles is an acronym for Cosmic Assembly Deep Extragalactic Legacy Survey, blah, blah, blah. What it really is a huge project to study the development of galaxies over time. They got more orbits on Hubble than any other project in history. Over 900 Hubble orbits. And they looked at 5 different fields, looking very deep into these fields. All right, and here is one of them. It's called the Ultra Deep Survey. And this is filled with about 30,000 galaxies. Okay? And these galaxies are spread out across space. But as we look out into space, we're also looking back into time. If you look 1 billion years out into space, you're seeing that galaxy as it was 1 billion years ago. If you go 3 billion years, that's 3 billion years ago. Some of these galaxies are 10, 11, 12 billion light years away, so we're seeing them as they were 10, 11, 12 billion years ago. By statistically looking at those galaxies at different distances, we can assemble a view of galaxies as they were at different ages of the universe, which gives us a picture of how galaxies develop. So they gave us this data in the Office of Public Outreach, and we said, well, the first thing we want to do is we want to show people those galaxies at different distances. So we created a visualization by cutting out every one of those 26,304 galaxies in the catalog, and then placing them into a computer model at their correct relative distances. Now, we didn't put them at their absolute correct distances because then it would be so long that the fly-through would take probably 2 hours to do. We want to do it in a minute or so, so we compress them in the z direction. But we do have a relatively scientifically, the relative distances are all proper between the various galaxies, okay? Can we take the lights down so people can see this, because there's a lot of black here. Take the lights down. There we go. That look better to you guys? Okay. And so here we have the visualization of the candle's ultra deep survey field. So that was our experiential visualization for the Candles Ultra Deep Survey. We also plan on doing some didactic ones where we'll have narration and point out some of the really cool features of it, or the scientific features of it. Do we have a question there?
It seemed as if you weren't traveling in a straight line. There was some steering going on. Is that
yes, the camera did not fly in a straight line. I actually choreographed the camera to fly up near that one white galaxy, then down through that cluster, then swoop through to those 3 red galaxies, so that you would, add some. I sort of thought of it as a roller coaster ride through galaxies. Yes, question.
How fast are you going?
You're traveling about 13 billion light years in a minute and 13 seconds. So you're violating every known law of physics. All right. So each object that you saw in there is a galaxy. We cleaned out all the stars and all the other artifacts from it. And we're left with 26,304 galaxies, for which we had both an image and a measured or estimated redshift from the scientific team.
So at the end, there was very few. Is that because there weren't any galaxies then, or we couldn't see them?
That's a great question. So at the end, we went to black. We got to the end of the data set. We got to the greatest distance that Hubble can see, because galaxies further than that, their light is redshifted into the infrared, and Hubble can't see them. But what telescope will be able to see them? Webb Space Telescope, okay? One of the reasons we want the JWST is to look deeper into the universe, because the light from those galaxies is in the infrared, and JWST will be able to see them with similar resolution to what Hubble has. All right? Okay. Now let's go to our featured speaker tonight. Our speaker tonight is Bonnie Meinke. She joined us about 5 years ago, and she has been in the Office of Public Outreach ever since that time. But about a month ago, she got a new position. She, in the Office of Public Outreach, she was one of the liaisons with the JWST team. She's now moved over to the JWST Mission Office team and is now a liaison to OPO. So she sort of just jumped over the fence and is working with them. She is an expert on Saturn, as you will hear tonight, having done her PhD at the University of Colorado, yes, and having worked at the Rubin H. Fleet Science Center. Yes. See, she didn't give me her biography. She was late just to come here, so she didn't give me her biography. I have to do this from memory. And she's overall a wonderful.
I've been here for 5 years.
Overall a wonderful person. Ladies and gentlemen, please welcome Dr. Bonnie Meinke.
Thank you, Frank. Okay, it's yours. This one's mine. Okay. Hi, everybody. I am overwhelmed and a little intimidated by the audience size tonight. No pressure. And lots of familiar faces. I'm very happy to see them. Yes, so Cassini, sadly, just ended. How many people tuned in for some of the big events surrounding the grand finale? All right, lots of Saturn files out there. I have no idea what's going on. Oh, Frank's the fixer, thank you. And yeah, so like Frank said, this is a mission that launched almost 20 years ago. It was October 15th, 1997. There are people in the audience that weren't even alive then, I suspect. Then it got to Saturn in 2004. And I remember when that happened, I was a fresh-faced grad student, and I thought, hey, this is going to be my mission. And I kind of can't believe that it's already at its end 13 years after that. But one of the really amazing things about the Cassini mission is that it didn't just change our view of Saturn. It changed our view of our solar system and of solar systems everywhere. So I'm going to walk you through the grand finale and the tour of everything Cassini learned as a way to bridge to the other types of planetary science that we now know about, care about, are dedicated to studying, okay? And I'm going to cut to the chase. I'm just going to go ahead and lay it all on the table. The biggest discoveries of the Cassini mission, icy moons. We knew about a whole bunch of them before we got there. We discovered more, and we discovered, of the ones that we already knew, really amazing, cool new things. Planetary rings. Of course we knew about Saturn's rings. It's the ringed planet. Everybody knows about this. Galileo studied it and thought it was amazing. We've learned a whole lot of new stuff in the last 13 years about those planetary rings that we didn't know, a decade ago. And then finally, the planet itself. I think that the rings and the moons get so much attention that the actual planet itself gets ignored in some ways. But it has all kinds of storms, big hurricanes, all kinds of wind patterns, really some interesting things. Those from, a geologist is excited about those. A meteorologist is excited about those. A dynamicist, an celestial mechanics enthusiast is excited about those. And so I'm gonna step you through these big discoveries. Because like I said, they fundamentally changed our view of Saturn, of our solar system, and of other solar systems. And I don't know why my slides keep jumping around. Okay. So I'm going to set the context a little bit for you guys, show you the Saturn system. So this, of course, is Saturn, the big planet here. These are the rings. You have the classical rings. Those are the things Galileo saw. Big, icy, bright, pretty rings. But those continue outwards as we skip through some of the moons. And there's an arrow here. Lots and lots more moons out this way, including the biggest moon of the Saturn system, Titan. How many Titan fans are out there? Yeah. Okay. I hear there's some theories about Titan. So I got to follow up with you guys tonight about new ideas about Titan. Okay. We have that big, pretty planet. It's mostly hydrogen, helium, similar to Jupiter, more similar to Jupiter than it is to Uranus and Neptune. But as I'll show, Saturn tells us a lot about all of the giant planets. Like I said, those broad, dense rings and the big dusty rings. And in between, there's a bunch of gaps. Those gaps actually tell us a whole lot about other solar systems. So I'll step you through that. And finally, all of these cool moons. So many moons. Okay. Let's start out with basically the atmosphere. The storms that happen, the weather that happens on Saturn, and what we've learned with the Cassini mission. So it's changed our view of Saturn. We got there and we knew the atmosphere was going to be interesting, but from distance, it's not as dynamic looking as what Jupiter has. Jupiter has those big, exciting bands. It has the great red spot, this giant hurricane that's lasted for years and years and years, for centuries. We didn't think Saturn was going to be that interesting. We were wrong. Scientists love being wrong. It's changed our view of our solar system because there's other giant planets, as I mentioned. There's Jupiter, Saturn, Uranus, and Neptune in our solar system, and those also have these really complex atmospheres that we can now tie what we've learned at Saturn to. And finally, it's changed our view of other solar systems. So over the course of Cassini's lifetime, we have seen there's a lot of exoplanets out there. I'll take you guys through a little timeline later, but when Cassini launched, we only knew of 5 other exoplanets, 5 planets around other stars, other worlds beyond our solar system, 5. One handful. And now we know of thousands. So learning about the types of planets we're seeing elsewhere is so important. And Cassini helps us study that. So let's dive into the atmosphere here. And this is probably the most iconic of the Saturn as a planet images. This is known as the hexagon. And I'm not talking about France. I'm talking about this amazing structure here. If you notice, it's 6-sided. 1, 2, 3, 4, 5, and 6. This is the North Pole right here. So this is looking straight down onto Saturn. And you can see in this false color or representational color image that there's a whole bunch of structure here in the atmosphere. These are all different storms, knots of different wind patterns and density clusters inside the atmosphere. And you can think of, this looks strange. We thought we had seen it with other means, other observations, both ground-based and a Voyager flyby. We thought we'd seen this hexagonal structure, but we weren't really sure, and it didn't quite click. We weren't sure why this would exist and if it could exist for decades. But now we know it's there. We confirmed it. And one of the cool things about the Cassini mission is it has several instruments, and each one of those instruments looks at a different wavelength of light. Basically a different color of light, some of which our eyes can't see. And some of those colors help us look through things. So this is actually an infrared image. It looks down into the layers of Saturn's upper atmosphere. And we can then see that the thing that makes this hexagon, this pattern of airflow, is a jet stream. There's a jet stream at a lower level of the atmosphere that is causing this pattern to be set up. This is actually kind of like a standing wave. If you've ever had a rope with have another friend hold the other side of the rope, like a jump rope, or had it connected to a wall, and eventually you can just get to go up and down, up and down. So instead of just doing this, the rope just goes up, down, up, down, up, down. That's a standing wave. The pattern actually really doesn't change. This is a standing wave, except it's huge, and it's six-sided, and it's really interesting and also, coincidentally, beautiful. Really cool. So we learned lots about what's going on with the interior structure of Saturn this way. Oh, and if you look closely, you'll see this part right in the very center, right at the North Pole. This is what's been called the rose, because it was cleverly colored in red in this representational color image. And it does look like a beautiful rose. This is a giant hurricane right at the North Pole. And this has told us a lot about how giant planet atmospheres might work. Because we're not just, again, remember I said that different wavelengths of light could probe different levels of atmosphere. That means we can see vertical structures. Being able to see how tall a storm is really important to understanding how it forms, how it works, the dynamics of it. Have you guys ever been out on a summer day and you see a thunderstorm forming in the distance? And you see the clouds billow up and it forms kind of an anvil shape. And then you say, oh, I better get inside, or I better drive home from work right now because that's going to be a huge thunderstorm and I know it's going to rain and I know there's going to be thunder and lightning. I better get home. That's the same kind of thing that we're learning about here. That vertical structure is really important to informing us how this works. Another example of the amazing storms we've seen on Saturn is this guy right here. You can kind of see it starting to form over here. This is regular, quiet Saturn. Nothing too exciting happening. Like I mentioned before, no huge bands. Typically in regular visible light, Saturn looks kind of yellow, kind of orange. Nothing big and bold happening. And then we see a storm form. And slowly that storm creates a wake as different layers of the atmosphere move around it. And you can see this time series where then it keeps going along into a long band, and it wraps itself all the way around Saturn. And eventually you have a very interesting curly fringed band. So that's telling us, we've learned a lot. This happened over the course of several months. And this thing lasted a couple years, I think. And so through this, we were able to really learn about how storms form, how they persist, what may be causing them to die out and quiet down. So this also tells us about stuff on our own planet, right? We know about hurricanes. Hurricanes exist on Earth. And when you're over the ocean, especially when it's warm, you have the moisture, you have the heat. That hurricane can build up and build up and build up and get really strong. But the second it hits land, you lose the moisture and it may die out. The second it goes too far north and it hits some cold water, it may die out. So what a storm that persists is telling us is what's going on underneath. What is giving the storm its power? What is driving that storm? So learning about how these work on Saturn really tells us a lot about how these work elsewhere. For example, Jupiter. So toward the end of the Cassini mission, we have the fantastic sibling spacecraft that goes out to Jupiter called the Juno mission. And Juno mission has JunoCam, which is actually a public outreach instrument. Was not intended for science, but we're seeing some amazing images come back from it that we're doing some science with. You can compare this sort of storm on Jupiter. You can see some vertical structure there, some other interesting things, to what we've seen on Saturn. Or you can look at things like this. This is Neptune. Every image I can see in the first 3 pages of a Google search on Neptune images is this image or some version of it. It has this big storm here. And I know Frank's talked about this storm before, I think in a News from the Universe or something before at a public lecture series. That storm doesn't exist anymore. It hasn't existed for years, and we know this. But this is such an interesting image that this is the Neptune image that everybody associates with it. This storm probably only lasted a few years, but Neptune is different than, say, Jupiter. Neptune is farther out from the sun, so it's cooler. It's made of different stuff, like there's ammonia and some other, it's not hydrogen helium like Jupiter and Saturn. Lots of other things going on in the atmosphere. So what we're learning is, by looking at just the 4 examples in our solar system, atmospheres are different. There's no cookie cutter formula for how these things work. And now that we have thousands of candidates of exoplanets, many of which are gas giants of some sort, we can now start to put the pieces together and learn more about how these things work. And not expect, as scientists who model these things, can't expect them all to work the same way, especially when they're in different circumstances. Say you have a gas giant that's a hot Jupiter. Who's here heard of a hot Jupiter? That's something roughly Jupiter-sized. That's really close into the star, closer than Mercury is to our sun. So it's really hot right there. So hot, in fact, that the atmosphere could bubble away, could evaporate away from the heat of the sun. It's so close that it's tidally locked. That means there's one side that's always daytime, one side that's always nighttime. It could be really far away and be very, very cold, but still really big. What happens there? We need answers to these, and so studying what I call our backyard laboratory of our solar system is really important. Because now we have all these candidates. We want to know what's going on with them. We want to know how these work. We also are finding out compositional information every day. The Webb telescope is going to tell us what these atmospheres are made of. And we need what we call ground truth. The Cassini mission has given us some ground truth, some really concrete evidence nearby of something that we know of, that we have observed for a long time, and we can compare to. A term I'll use later and throughout this talk is comparative planetology. So that's really important for what we're doing and what the Cassini mission has contributed. Okay, on to planetary rings. You thought I talked a lot about atmospheres. Wait till you get me started on planetary rings. I love planetary rings. That's my background. I'm all about the rings. So for Saturn itself, we weren't really sure about the rings when we got there. We'd seen some cool stuff with Voyager. We'd seen some cool stuff from the ground. But we weren't really sure. What we've learned is the rings are ancient. They probably formed with Saturn. They're massive. They're probably, a fractional size of a moon, which is way bigger than we thought they were going to be. They have all kinds of complex structures inside, including small moons that we call moonlets. They change on small timescales, human timescales, Cassini lifetime schedules, which is unheard of for astronomical objects. We're not dealing with millions and billions of years for a change. We're talking about weeks, months. I once did a paper where I measured how things changed over the course of 28 days. What? The grass in my yard at home grows on the same time scales that some of these things happen. Thank goodness I don't have to mow the rings. Okay. It also changed our view of our solar system. Saturn is not the only planet with rings. Jupiter, Uranus, and Neptune also have rings. They're different, but now we know that ring systems are not necessarily temporary. This makes sense because we see them around all 4 of the large planets in our solar system, so it clicks. And these rings are constantly evolving. Again, helping us piece together the puzzles for these rings, especially on Uranus and Neptune, that we haven't gotten a really good look at. We've only gotten some Voyager data back from them, so we really want to know more. And finally, told us about other solar systems. So I'm not talking about the ring systems in other solar systems. I'm talking about the disks that surround those other suns that planets are born from. The rings are an excellent example of an astrophysical disk. And another example of an astrophysical disk is a protoplanetary disk. The gas and dust and debris that forms new planets. And by looking at Saturn and the rings and how moons form in those rings, we can learn about how complex worlds are built in the debris disks around new stars. Okay, let's set the context again. Broad, dense rings, the classical rings A, B, C, the gaps within those classical rings, and then this huge dusty component which encompasses the E, the G, and the Phoebe ring. All right. And what are Saturn's rings made of? They are made of water ice. So for those of you from Philadelphia, I apologize. It's not some delicious treat. When I say water ice, I'm talking about H2O. So this is actual ice that is in all kinds of sizes. So it's huge distribution from dust-sized grains of ice all the way up to things the size of cars and houses. These things are constantly moving, smashing into each other, sticking, and then those things are hitting each other and pulling each other apart. This is a constant swirl of activity. And what the Cassini mission has really shown us is how dynamic these rings are. That this process of smashing and accretion and destruction is constantly happening. Okay, so what we're really learning is that the Saturn system is not a ring system. It is a ring-moon system. And these rings and moons are constantly doing a dance. There are 62 named moons at Saturn, but I like to say that there are billions and billions of moons at Saturn because each one of those little particles in the rings is a moon. They're all orbiting Saturn together in this beautiful dance. So let's zoom into the outer B ring edge, and we see vertical structure. The Cassini mission was there for equinox. Equinox is when the tilt of the rings perfectly lines up with the plane of our solar system, so that the sun is perfectly on edge, and so that means that it casts shadows. Anything sticking up from that flat plane of the rings is going to cast a shadow. This really helped us because we saw at the outer edge of the B ring, we saw mountains. These are all mountains. And it's not an even distribution. It's really, really kind of funky looking, no symmetry. These are, I said these are mountains. These are thousands of feet tall. And we see those cool shadows coming out from them, so we know how tall they actually are. So then it comes down to the dynamicists. And we dynamicists looked at this, and we tracked out where other moons were. We tried to figure out what was causing this, and we said, that's no moon. Well, actually it is. It's called Mimas, or Mimas. People say it both ways. And this is a moon that's just outside of the classical rings. That's where its orbit is. And it picks on the ring particles. It tugs on them just a little bit with its gravity. Tug, tug, tug. And just like you might have a tub of water, and when you move it back and forth, it actually sloshes so that stuff comes up. The waves come up out of the tub. That's what's happening here. So we have vertical structure because of the sloshing that Mimas causes. So this causes vertical, but if you were to look down on a vertical, you'd really just see a density enhancement. So you'd see a big clump of stuff. It's very thick there. And when we look at other solar systems, other forming solar system, we see a disk around a star. So this is where that star would be. This is the whole disk. And you can see that's not a pretty uniform disk. There are bright spots here, kind of over here, and empty spots up here. That looks surprisingly like the kinds of weird structures we see at the B-ring's edge. So a ring scientist sees that and says, ooh, 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 there's a planet there. There's a planet. So what we can learn from rings applies to protoplanetary disks, to debris disks, that sort of thing. Just for comparison, this is really big. This here would be Pluto's orbit in our solar system. So you can match how big this disk really is. And a dynamicist can map that and figure out where to look for the planet in this system. Okay, so let's go back to Saturn's rings for another example. Out to the A ring. The A ring is where we see these gaps. And we knew about this before Cassini. We knew there were two gaps in the A ring. There was the Encke gap and the Keeler gap. And the Encke gap was big enough to really see pretty well. The Keeler gap was very thin. With the Encke gap, we saw a moon. We call that Pan. And we thought, we didn't know what Pan looked like till we got there, but basically it's a sad, twisted little potato. Maybe the size of Manhattan Island, something like that. But we only saw the Keeler gap. We didn't see anything inside of it. So we thought, well, what else could clear this whole gap? There must be a moon there. So Cassini looked for it. And Cassini found it. In this gap, this Keeler gap that is only about 40 kilometers wide, we were able to find an even smaller, even sadder, even more twisted and rotten potato. And so we gave it the lovely name Daphnis. And we learned something else. Because the Keeler gap is so small, you can see Daphnis pulling on the edges of it. Oh, you can see it kind of here. And this structure, again, it's the same kind of structure that happened in the outer B ring, that vertical structure. There's a wave or a wake, kind of like if you think of a boat going through water, something very similar is happening there. Same kind of mechanics over with Pan that it disturbs in the Encke gap. And so we know this kind of thing happens. Moons form within the rings, and they can clear large swaths of the rings. So again, let's take that out to our galaxy. Let's take that to other stars, because we see debris disks everywhere. And when we see a debris disk, like we did here with Hubble, we see a big gap around this particular star in its disk. Again, a rings person says, ooh, there's a planet there, there's a planet there, I know it. So you do something, this is an illustration of what could be happening here. The same kind of ring exists. So now we have a place to target our observations. A mission like the James Webb Space Telescope, will be able to do a good job of looking for a planet in there if it's big enough, because the dust and the gas and the debris disk will the infrared light of the star may be able to pierce through it. So, and plus it has a coronagraph that'll block out the star, so we might be able to see it that way. Plus, there's all kinds of other, like I said before, other systems in our solar system. There's Uranus and Neptune here. Very thin, very dark rings, but they can teach us something as well. And the lessons learned at Saturn with Cassini can be applied here to learn what's going on. We think that there are moons being created in the ring system of Uranus. We've seen rings change since Voyager at Neptune. So we know things are happening, that these are dynamic rings as well. So people who worked on the Cassini mission are now turning their attention to Uranus and Neptune, especially using Hubble and putting in proposals for the James Webb Space Telescope to be able to study what's happening in those systems. Our solar system itself has two astrophysical disks. We have the asteroid belt, which is here between Mars and Jupiter, something like this. When we have the Kuiper belt, which is out beyond the orbit of Neptune, kind of where Pluto sits. And both of those are remnants of our solar system, of the formation of our solar system. And by looking at those, by studying those, we can tell what happened in the formation of our solar system. And learning about the dynamics of the Saturn system, applying that to our solar system and what it looks like now, we can start to put the puzzle pieces together. For example, there's an interesting dynamical thing that probably happened in the asteroid belt, a resonance, that is evidence that the four giant planets used to be closer in together, and that they jiggled out, separated, and while they were doing that, Uranus and Neptune probably swapped spots. So tracing out the dynamics of these kinds of astrophysical disks is really important for us understanding our own solar system. And as I mentioned before, we know of all these debris disks, protoplanetary disks across our galaxy that we can apply lessons learned to be able to learn how planets are forming, target where to find them in the disk, and we have all these new telescopes coming up, including the James Webb, where we'll be able to look into these dusty disks using infrared. All right, so really, this is my mantra, Saturn's rings are a natural lab. We must go back. We've learned so much already, and we can learn more. Okay, and finally, the third point, icy moons of the big discoveries. So the icy moons we knew about, but we didn't know until we got there that Enceladus has plumes, meaning geysers, something like Old Faithful, which we like to call Cold Faithful, by the way. Titan has lakes. This big Earth-like moon has lakes, liquid lakes. We didn't know that before we got to Saturn, before Cassini got to Saturn. So then we changed our view of our solar system because we realized icy moons can be geologically active. We didn't think that was possible. We thought icy moons were just hunks of ice left over from maybe the formation of the planet itself, or maybe they were captured from the Kuiper belt, or some kind of lone comet that got trapped. But no, this is really interesting. And then when we apply it to other solar systems, we realize geologically active moons could harbor life. They could be warm enough that we're getting the right environmental conditions for life to exist on them. And this expands our whole view of what habitability means, of what a habitable world is. Expanding those definitions is huge because astrobiology is a burgeoning field. even today, and we're learning new things every day, which Cassini has really helped point to. So again, setting the context, all kinds of moons going out from the rings, even more farther out that we don't have room for on this screen. But let's start with Titan. So Titan is the biggest moon of the Saturn system. Titan, at first glance, in visible light, just looks fuzzy and orange. That's because it has this big, thick atmosphere. Really big and thick. As a matter of fact, in one of the more recent Star Trek movies, the Enterprise hid inside of that hazy atmosphere because it's so good at hiding things in visible wavelengths. But once you get inside and look at it underneath those layers, both with the instruments that were on Cassini and with the lander that went down called the Huygens probe, we could see the actual surface of Titan. And we were able to make out methane lakes. These, if you look carefully, you study other close-up photos, you realize that there are shorelines. You realize that this is actually liquid, standing liquid. And you check out the chemistry of the moon, and you see that it's methane. So just like our Earth has a water cycle, where we have water on the ground, it gets heated up, becomes clouds, rains back down, seeps into the ground, into aquifers, and then comes back up into lakes, that kind of cycle. Titan has something similar, but for methane. What a bizarre and cool world. And as a result, it makes it the most Earth-like thing in our solar system besides Earth. This is fantastic. But it's also very cold. So I don't know that it's the best candidate for habitability, but it is stretching our thinking on what habitability is. Even if it's cold, it does have this liquid on the surface. It has lakes. It has dunes. It has sand dunes. Now, some of it's tiny pieces of ice rather than rocky type of sand that we have on Earth. But wow, it has winds. It has weather. It rains. Liquid methane again. But this is really fascinating. So we have a complex world here that we're looking at. Then, a little bit later in the mission, I actually got to be part of this one, so I'm really excited about this story. We were working with the team that does the imaging. Of course, the imaging team reaps all of the benefits on Cassini. They're beautiful images. Everybody loves the imaging science subsystem. But they see something around Enceladus, and they think, that can't be right. There's got to be something wrong with the detector. We hit some kind of anomaly in the feed that came back to Earth. We're not sure. But I was lucky enough to be on the UVIS team, the ultraviolet imaging spectrograph team. So we were like, okay, well, we took some images too, or not images, but we took data. Let us look at it. And we see there's evidence that there's something right around here. The infrared instrument does the same. The radio science instrument does the same. And we all confirm that this, whatever it was right here, is there. It wasn't just something weird that imaging picked up. So we go to work on it. And we realize that it's a plume. It's a series of geysers that are erupting out of the south pole of Enceladus. Now, Enceladus, by all accounts, is, yes, it is the brightest thing in our solar system because it's covered in pure white ice. But it's small. It's only like 250 kilometers across. That ice looks to be really, really thick. Why would it have geologic activity that would cause a geyser? But we've done studies. We've flown. Cassini flew by Enceladus many, many, many times, and we mapped it out. These geysers were there. These geysers changed position over the course of the Cassini mission. They gave us evidence that there's possibly liquid under the surface, and that these icy worlds that seem geologically dead are really interesting and active. We had hinted at this before. We weren't quite sure when we got there. We saw Enceladus buried in the E-ring, embedded in the E-ring. And we thought, well, maybe that's why it's so bright. It's in a ring of ice, and it gets the ice dropped on it every day, and that's what happens. But now we realize that ring is there because the plumes feed it. It is created by Enceladus itself. Enceladus is spewing out all of the contents of that ring. So that gives us a new outlook on how rings are created. Okay. And like I said, it's probably, we got some really close-up images after that, all these various geysers happening all the time. They, I don't know who's actually seen Old Faithful in real life. Okay, it goes up maybe a couple hundred feet at its highest point. This, however, goes up kilometers. It goes out almost as tall as Enceladus is wide. So that's how it feeds the E-ring. It's phenomenal. And we realize, tracing back the dynamics of how that must work, that there must be, underneath this thick ice shell of Enceladus, some sort of hemispheric-sized lake of liquid water that is feeding it, and it stays warm. So then we think, oh, well, if that one's active, let's look around the solar system. People have, for years, loved Europa around Jupiter, and we've thought, oh, Europa could have subsurface activity. We think that it has a thin ice shell based on gravitational data from the Galileo spacecraft. We think that it probably has a subsurface ocean. Let's look at it, see if it has any geysers. So Hubble looked at it, and bam, sure enough, we see evidence for water in certain areas at certain points of its orbit, which means it probably has some kind of periodic geyser that's coming out of, again, its south pole. Now, we're not sure on the South Pole connection, but that's interesting. And so you get something that's kind of like this artist's impression of what it might be like to stand on the surface of Europa, a geyser coming out of an ice field. Kind of feels like you're in Iceland. It's very cool. And the alternative is it could trap little under crust lakes full of this stuff. The crux of it is there is heat below the ice. Heat means energy. Liquid water increases the potential for life to exist. So if there's energy and liquid water, perhaps there's life. And as we're thinking about our definition of what Earth 2.0 might look like, what another Earth might look like, perhaps we should be expanding our definition. Maybe it shouldn't just be a planet that is the size of Earth, that's 1 AU from a sun, that's a G2 type star. Maybe we should start thinking about ice worlds and moons around giant planets and those sorts of things. So as we look across our solar system and as we look at other exoplanets, we need to have this in mind. So Cassini has given us this great gift of expanding our vocabulary to what habitable means. So I promised you a timeline, just to put this all in context. Again, we had almost 20 years ago to the day, in 2 weeks it'll be 20 years ago, the launch of the Cassini mission, Cassini and Huygens together. And there were 5 known exoplanets. So Cassini was truly just a Saturn mission. It was there to learn more about Saturn as a planet. Then, when in July 2004, when Cassini got to Saturn and did its orbital insertion, there were 12 exoplanets. Ooh, 12. I remember that feeling of, oh, this is about to happen. This is so exciting. But Cassini is still just a Saturn mission. But it will be really cool if we learn about like 15 or 20 exoplanets. And then in between 2004 and today, We've had the Kepler mission. We've had Hubble looking at stuff. We've had lots of ground-based campaigns looking for other worlds. And so today, we know of over 3,600 exoplanets, with so many more planned to be observed. Those are on small patches of the sky. We know more exist. When you look up in the sky at night, you know that for every star you see out there, on average, there's at least one planet around that star. And so now we can apply these lessons we've learned over the course of the Cassini mission to all of those worlds, especially since some of those systems have more than one planet. So we're looking at ecosystems, whole solar systems that are forming in much the same way that perhaps the Saturn system did, and we can apply those lessons to figure out how these worlds form. And like I said, we know of even more protoplanetary disks, these disks where planets form. So, getting back to that first slide. So these icy moons, we've learned, are geologically active with the Cassini mission. And this has given us the idea that they are bastions for life. We need to start looking there if we want to find life beyond Earth. We have seen planetary rings that are ancient. They probably formed with the planet. They are active on short time scales, and they are dynamic. They're constantly changing. These are a model for how worlds are both built and destroyed in our system and beyond. And the weather, the storms, the incredible complexity of Saturn's atmosphere has helped us understand that the atmospheres of other giant planets are just as complex and dynamic. And we can't have one computer modeling code that we use as scientists to model all of those worlds beyond our own. So really what it comes down to with the Cassini mission is using our own natural laboratory in our backyard for answering questions that are fundamental to us as human beings. How did we get here? Looking at the rings. How does the universe work? Looking at things like storms on Saturn. And are we alone? Looking at icy worlds beyond our own. So I think that the legacy of the Cassini mission will be felt for years and years. There are many research projects that have yet to be done with the data Cassini collected, and many that have results that have yet to be fully felt and impacted in other branches of astronomy. So I think as we go forward together as humans and as a scientific community, we can really come back to the Cassini mission and thank it for everything it gave us. So, thank you. All right, I see hands. Do you want to moderate or do you want me to?
I'll help moderate.
Okay, go ahead.
All right, let's take somebody in the back there. Yeah.
What are the dynamics that determine the height of the rings and the structure?
What are the dynamics that determine the height of the rings and structures?
So the thickness of the rings itself is determined mostly through angular momentum. That's the same thing that when you have a ice skater that's spinning around and he or she brings in their arms and they go faster. It's the same kind of thing. So nature loves a frisbee. Everything wants to be a disc. And so as things rotate around the central point, they spread out into a disc. Now, when we have other actors in a system like a moon, those moons can affect each other. So in the rings, all those little moons that are the ring particles get smushed together or spread apart by a big moon coming in and throwing its weight around. Say, no, you move over here, no, you move over there. So sometimes you get them crashing together and, like I said, sloshing up through vertically, possibly also colliding into each other and sticking together, and in some cases being ripped apart really far. So there's a couple of things at play there that result in just the overall structure of the rings, but also these small scale structures.
Okay. There.
Where does the water come from?
Where does the water come from?
So this is one of the things that Cassini has really been trying to figure out. So I'll give you a little bit of history. Before we got there with Cassini, we thought that the rings were likely delivered by comets. Comets, we know, are have a lot of water content in them. They were probably streaking by the Saturn system. Saturn's big enough that if they got close enough, it could rip it apart. And voila, you've got a bunch of icy ring particles in orbit around Saturn. There were different people debating what influx of comets must there have been to create such vibrant rings. And if this was true, and these would still have had to be pretty light rings, less massive, then they would have, over time, been able to, those little ring particles spiral into Saturn until that entire ring was depleted and there was no more ring. And the time scale on that was something around 50 to 100 million years, so roughly the age of the dinosaurs. Well, why then are we lucky enough as human beings on a planet in a solar system that's lasted billions of years? Why are we lucky enough to be able to see this now? So that's one of the arguments against them being young. But there was no evidence for them being ancient until we got there. And so now we see that they are in fact quite ancient both spectroscopically and by the dynamics we see. We see them effectively recycling. So moons build up and then they break apart. So rather than all these particles spiraling inward because they're constantly particles, they come together and there's kind of like a reservoir of ice in a moon, which then gets smashed back apart, and then the process repeats. So maybe they're ancient. Maybe they formed with the Saturn, the planet itself. So then the question becomes, well, then how are they replenished, and where did that ice and water initially come from? The current biggest idea, best idea, most liked idea is that the initial system had a lot of large moons, ice moons. So something similar in size to Titan, probably had half a dozen of these, and those slowly moved in closer to Saturn and were over time ripped apart by tides and helped replenish the ring system, because we've seen that the rings are actually quite massive. So that makes sense to us right now, and so we're left with Titan as the sole survivor of this family of moons that probably is responsible for the rings continuing to exist.
Okay, down front in the orange.
Yes, I read one of the articles in the Post that Cassini had sniffed carbon in the Enceladus plume. Is that correct?
So the question is, I read that Cassini had sniffed carbon from Enceladus. Is that correct? I'm not 100% sure on all of the constituents that it sniffed in the plume. It has found a lot of stuff. I know that there's sodium that it's found, which is evidence of salt, which would make sense since it's liquid, and a myriad of other things. I'm sure carbon is in there. So yeah, lots of stuff in there. I know some of the stuff that most recently in the plumes that they're finding are in that plume besides water. They're finding exist in what are underwater vents on Earth, these deep ocean vents where we see lots of life, very small bacteria all the way to like little blind crayfish and that kind of thing. So
finding evidence of those sorts of materials in the plume lets us know where the plumes may be coming from ultimately, and that's really exciting. And I think carbon is one of those that would give us evidence of them happening farther down, deep down, and the kinds of materials that are at those undersea vents.
Okay, other questions? Lots of them. We have a lady down front. I'd like to add some gender diversity to it.
Does the hexagon shape ever change to non-hexagonal?
Does the hexagon shape ever change?
Not that we've seen. So far, in all of our observations, we haven't seen a change. Over 20 years. There was some evidence of the hexagon being there even prior to the Cassini mission, both through ground-based observations, and Voyager gave us a kind of a skewed view of what we thought might be the hexagon. So we thought it was there, which now builds up evidence of something more like 40 years of it being there. And our resolution wasn't good enough to know if it was there before we started looking for it. So we think it's very long-lived, and we haven't seen evidence of it changing over that time period that we've been looking.
Okay, over here, yes.
Do the points of the hexagon rotate?
Do the points of the hexagon rotate?
No, they are fixed with respect to the planet. Yeah.
Unlike the storms.
Right, the storms move around. We see them actually move, even with respect to rotation, but that hexagon is fixed. Because it's, like I said before, it's a standing wave, so it's fixed.
Okay, in the blue there?
Question about the end of the Cassini mission. How deep did it get before it burned up, and did we get some useful data at the end?
I
So
don't
how
know.
deep did Cassini get into Saturn before it burned up or whatever it did?
I don't know how deep it got, but we, unfortunately, because of how it was going in, we tried to position it so that we would send back data, but there wasn't much time for that. The data that comes back from the Cassini mission, as with many deep space missions, if you'll recall, New Horizons was this way too, very, very slow trickle of data. So that's why when we first saw Pluto with New Horizons, it was still grainy and fuzzy, and you had to wait a couple of weeks. That wasn't just data processing. That was actually getting the data to Earth.
The interplanetary internet is like your 28.8 baud modem from 25 years ago.
So that's a big part of it, yeah. So we really didn't get it.
Okay, back there.
Yes, you.
The hurricanes are short-lived. Is the polar hurricane short-lived?
So the hurricanes are short-lived. Is the polar hurricane short-lived?
I don't think so. I don't think so. With respect to like the one that was there in the northern latitudes that ended up wrapping around.
So does that affect the hexagon shape?
It shouldn't. The hexagon shape is set up by what is effectively a jet stream. Same way we have a jet stream on Earth that brings us some extra cold winter weather in the winter. But I will say I'm not 100% sure because I'm not an expert on that particular storm, so I don't know how long it's been around.
Okay. Over here, blue.
There's a theory that Europa's water is liquid because of the interaction between it and Jupiter, the gravitational pull of Jupiter. Is that also true between Saturn and Enceladus?
And Enceladus, does it is its water due to gravitational interactions with Saturn?
Right. So that's one of the things we're still trying to figure out. The gravitational interaction being kind of the tidal compression that happens. The same way we have tides on Earth, water coming in, water going out at the beach. Something similar happens with Jupiter, except it's way bigger, and its moons, which are a little bit smaller. So effectively, it squeezes those moons, and that squeezing adds energy to them, And that energy can then liquefy ice to be water. At Jupiter, it makes sense because these are very close-in moons. Jupiter is really big, and they're in what we call resonance, right? So there are special orbits that are particularly susceptible to this. Enceladus is not. Saturn is a smaller planet. And we think Enceladus has a larger ice shell than Europa does. So it would be harder to squeeze. So we're still trying to figure out exactly where this heat is coming from. It's possible that it's some sort of primordial heat, either formation heat or radiogenic heat, although those don't quite add up to the amount of heat that would be necessary. It's also, there are people who propose something called clathrates, which would be kind of little trappings of water that just kind of have to pump and release the water. There's some folks who think that they've accounted for all of the energy necessary to liquefy a hemispheric-sized lake right there, but they're not sure. So, and again, it comes back to this thing of us being special. Are we living in this very special time where Europa is or Enceladus is active? Are we really that fortunate? And if so, then you look at Europa, and Europa is also active. Wow, we're like doubly special to be living in a time where both of those are active, and this, or maybe the actual situation is that this activity is just ongoing and always happens, and we're not special. So, sorry, scientists tend to think we're not special.
Okay, orange shirt there.
In that hexagon image, at about 4 o'clock or so, was a fuzzy white dot, and about 9 o'clock was a funny little, looks like a little miniature spacecraft, actually. What? CIA spacecraft.
Can you repeat it?
So, in the hexagon image, right. About 4 o'clock, there's some kind of, let me just slide back. At 4 o'clock, there is, there we go, yeah. Okay, at 4 o'clock, there's this thing. I don't know, that's 5 o'clock, I'm sorry. There's this kind of blobby thing. And then over here at 9 o'clock, there's this thing. What's going on? Well, this is definitely some sort of other storm and disturbance that's happening within this structure. This isn't this is a shape, but this isn't the shape here. Definition of the shape doesn't control what's happening in here. It's like a wall, and it confines some of the things inside of that wall, but it doesn't necessarily make things happen in that wall. So this storm, this is a storm. It may not be related to the hexagon at all. And this, I don't know. Maybe that's an artifact. I have no idea. I don't know. I can see, well, too bad it isn't a dark storm, because then you can call it a 5 o'clock shadow. Oh!
All right. Anyway, you have a question down here.
I have 2 questions. One, why did they crash?
Why did we crash? And
the second one is, where's Earth's ring?
Where is Earth's ring?
Both good questions. Okay. Why did they crash? Something called planetary protection.
The time direct. Wouldn't it be better to let it stay there because we saw it in the equinox?
Okay, so let her finish her answer.
So a lot of people are like, well, it was still going. Why couldn't we let it keep going? NASA in particular wants to make sure that we keep the system clean. We know that with Enceladus's plumes, we know that there's a possibility for life in the system. We don't want this spacecraft, even though it's clean by our standards for launching spacecraft, we don't want it accidentally smacking into one of these moons and either destroying life there or contaminating it with our life so that we can't tell what's happening when we go back. That's really important for us. The folks at Mars undergo a similar planetary protection protocol. The Galileo mission also crashed into Jupiter for similar reasons. So this is a long-standing practice, just for making sure we don't ruin our own experiment as scientists.
Like the Earth. I'm just kidding. Exactly.
All right, we got a guy who's standing who has a question. I'll let somebody who's standing have a question.
What was your second question?
Sorry,
where's Earth's ring?
Oh, I like the where's Earth's ring thing. Earth had a ring. When the moon was formed, something crashed into the Earth and kind of ripped off the top layer. It was probably a ring, but it coalesced into what we now know as our moon. So this is why we thought the Saturn rings were young. But ultimately, I think it comes down to, in part, we have a moon, and our moon is big enough that it would keep a ring from forming. 2, we are small enough as Earth not to have a significant natural ring. And 3, we do have rings, all kinds of satellites that we've created and put up there.
What about the other terrestrial planets?
Oh, none of them have rings.
No, the small planets formed by planetesimal accretion versus the disk accretion for the giant planets. Yes?
You mentioned in your presentation that hurricanes feed on heat. This is a north-facing hurricane. What is the energy source?
Okay, so hurricanes feed on heat. What's the energy source to power the polar vortex here?
That is an excellent question. So just because it's northern facing doesn't mean that it was facing away from the sun. That's the first one. But Saturn itself has a lot of internal heat. That's all the giant planets have a lot of internal heat. They're far away from the sun. It really doesn't matter how much they're warmed by the sun. I'm going to take that back. It does matter that they're warmed by the sun. But for this particular thing, it matters more that the internal heat is there. Saturn is actually super interesting with its internal heat. It produces a lot of it because it's very dense, lots of gas layers, and as something that big eventually kind of settles out, the different gas layers settle out over the lifetime of the planet. Some of the heavier elements that are in the outer layers settle down. So basically, what can happen at Saturn is you could have liquid helium rain into the inner layers of Saturn. And that is energy. Those things falling in is energy, and that is heat, and that's the atmosphere. When we look at Jupiter, for example, that's another example. Jupiter's output of energy is greater than its input. The energy it absorbs from the sun is less than what we see radiating back out for the same reason.
Okay, we got time for only one more question. Do we have any kids in the audience with a question? Just I would like to give the... I know, you're young and
Don't let
hard.
the gray hair fool you.
Right, this guy in green here has been waiting the whole time. He gets the honor of the last question. Sorry.
My big interest is exobiology, and I'm just wondering, what are the odds for life on the moons, and are we going to send something specifically for life? Because I would say that that's really the ultimate question. That you hear about, but finding life would really be the biggest discovery.
All right, so the question was, what are the odds for life on the moons, and are we going to send missions specifically to look at those moons for life? Good question to end with.
Yeah, I would rank the moons of the solar system in terms of probability of life as Europa, Enceladus, Titan. Europa because it probably has the most heat, the shallowest crust, and the largest rocky core that could support some sort of chemoautotroph type organism at a deep sea vent, for example. But I can't put numbers on probability for that. The way to confirm this would be to actually go there with a submarine That's what I would like. Maybe something that could land, drill down. But even an orbiter or something would be very cool. The problem with that is the Jupiter system, full of radiation. You have to do what the Juno mission does. Come in quickly and go way far out. Come in quickly and go far out, or else your electronics are fried. So this is one of the tough things about a Europa mission, which makes the Saturn system a little more enticing, less radiation there. But I think, in the community's opinion, maybe less likely to find life. So what we can keep doing is we can keep compiling evidence. As scientists, we want evidence. And there's never necessarily a smoking gun unless we were to go there and pick up a whale. So...
that would be one strong mission.
Yeah.
Yeah, but I would just echo... I would echo what she said, is that, when we explored Mars, we first sent an orbiter, all right, and then we started to send landers and then rovers, et cetera. If we're gonna explore any of these moons, it's gotta be the same thing. We've got to send orbiters to map all the places that we might want to land, and then landers, and then rovers, and then diggers and submarines and such. So it's not gonna happen next year. It's not gonna happen this decade. It's a long-term process. All right, so we have to stop there. Next month's talk will be on dangerous worlds. So we'll take this even further. Ladies and gentlemen, let's give a real big warm thank you for Dr. Bonnie Meinke. Okay, last thing. Irini, raise your hand. Irini can take, what, 15 people? Yes. Okay. I know there's way too many more than 15, but when you have enough, just go. Do you want to hang out by this door? Okay, Irini's going to hang by this door. When she has enough, she'll take them across the street for observing. And if you don't make it this month, come back again. She'll do it every month that it's clear. Thank you all, and see you in November. And the boxes where you can subscribe or even unsubscribe to our mailing list and get the monthly reminders of the talks. And actually, also we send out the monthly listings of where it is on the webcasts. Okay. Announcements, yeah, sign up at the website, or you just give me your email address. And if you have comments or questions, you can send them to publiclecture@stsci.edu. If you would like social media, we have Facebook, Twitter, YouTube, Instagram, and maybe a few more things that haven't listed here. I myself am on Facebook, Google+, and Twitter every now and then, and have a blog on Hubble site if you want to follow me. The observatory, yes, the weather appears to be permitting tonight. And Irini sent me a text and said, yes, she will be doing it. So we will be meeting at that door over there, okay? Now, unfortunately, and it's really hard to tell an audience of this size, she can only take 15 to 20 people over, okay? And I know there's like 200 of you here tonight. So if you have been before, please let somebody else who hasn't been. And if you don't get to go tonight, please come back, and you will be able to do it after another lecture. Or you can go to md.spacegrant.org, find this web page, and they have open houses most every Friday evening, okay? They update this web page at like 6 p.m. or 5 or 6 p.m. on Friday to tell you whether or not it will be open, and you will get a longer observing session at their open house than you will get after the lecture here, okay? And as we're going into fall, we've just passed the equinox, the nights get longer, and so lots and lots of observing is possible, okay? All right, and now my part. News from the universe for October 2017. Unfortunately, the top story tonight is JWST launch delay. No, you got to do that all together. 1, 2, 3. Thank you, okay? So this is this is a drawing of the main belt asteroids. There are several 100,000 of these asteroids. However, also in that area are a lot of comets, a lot of short period comets. And we're going to talk about an object that is actually both. Here. So, in November 2006, they discovered an asteroid, and they called it 2006 VW139. That's the standard nomenclature that we give to asteroids when we discover them. And then they observed the same object in November 2011, and they found that it had a tail. And tails indicate that it's a comet. So they also gave it the designation of Comet 288P. All right, so it had both asteroid designations and a comet designation. Well, that's obviously an interesting object, so what are you going to do? You're going to take Hubble and you're going to look at it. And Hubble looked at it in August of 2016, and Hubble saw this. Ooh, what do we see? We see in the center not one, but two bright spots in the center. So as you can see, I've updated it to be a binary asteroid, 2006 WV139, and I guess you could call it a double nucleus comet, 288P. We have an object that appears to be two objects. Now, in examining it and trying to understand it, they estimate that it was a single object that broke apart about 5,000 years ago. And then the gases that are exposed caused jets, and then the two pieces moved away from each other. Okay? That also produced material that streams out as this tail. So Hubble looked at it not just once, but 5 times. And we looked at it in September 1st, and September 9th, and September 20th, and September 29th. And what do we see? We see the tail wagging. Okay? Yes, comets wag their tails, right? So here are those 5 images. But you can see they only occur over this time scale of about a month. Now, some of the change of the orientation of the tail is due to the different geometry of Earth and the comet, or asteroid, as it was. But over the course of a month, it wouldn't change that far. So what they really think is that it's also due to different types of particles being emitted. The larger particles are here. These are on order of millimeter size. When I say large, we're talking tiny, tiny dust particles, okay? This is a dust tail. The tiny, tiny dust particles, about 1 millimeter. Those are large in astronomical terms here. 1 millimeter in size are blowing off in this direction due to how they're being ejected. But by this time, the dust was mostly very, very small, about 1/100th that size, or 10 microns. And those 10 micron particles get actually pushed back by the radiation pressure of the sun. And so here is where the tail is actually pointing away from the sun, like a normal comet dust tail does. And here it's not quite pointing away from the sun due to the larger particles in it. So we have a really cool object that's part asteroid, part comet, and is able to wag its own tail. Kind of cool. All right, our final story for you is Candles in the Dark. Now, CANDLES is an acronym for Cosmic Assembly Deep Extragalactic Legacy Survey, blah, blah, blah. What it really is a huge project to study the development of galaxies over time. They got more orbits on Hubble than any other project in history. Over 900 Hubble orbits. And they looked at 5 different fields, looking very deep into these fields. All right, and here is one of them. It's called the Ultra Deep Survey. And this is filled with about 30,000 galaxies. Of the James Webb Space Telescope, it will be NASA's next great observatory. It is an infrared telescope with a 6.5 meter mirror, 18 segments. It will be launched and go out 1 million miles from Earth, so it is nice and cool and away from the influence of Earth. It'll have these great sun shields to also keep it cool. It will do amazing things. It will do things Hubble cannot do. But it won't do them on the time scale we had hoped it would do them, okay? It was slated to launch in October 2018. That is no longer the launch date. NASA had a press release last week, and I'm quoting from it. It says, is planning to launch between March and June of 2019. So it's about a 6-month slip in the schedule. It is not indicative of hardware or technical performance concerns. They want to make sure that, look, everything's going fine. We just want to make sure it's perfect because, unlike Hubble, we can't go out and service this, okay? So integration of the various spacecraft elements is taking longer than expected, all right? And they want to make sure they do it right. And one other thing in terms of the financials, the existing program budget accommodates the change in launch dates, so you as taxpayers are not going to pay extra for this delay. It's all within the program budget. They build a lot of contingencies into these plans, and unfortunately we've had to take one of those contingencies. So instead of October 2018, we're looking between March and June of 2019. It will be worth it though, okay? It really will. All right. Our second story, A Tale of Two Comets. Yes, so I didn't quite come up with a real Dickensian story to go here, but I just like the title. All right, so first of all, what we're talking about here is the asteroid belt, okay? This is the orbit of Jupiter out here, and in here in the center we have the orbits of Mercury, Venus, Earth, and Mars. In between where you see all these green things and the red things, those are joy to be your host. I am Dr. Frank Summers of the Office of Public Outreach. And we have an amazing audience here for you tonight, Bonnie. Saturn really sells, okay? So we have a packed house here tonight. We may not have any more. We have a couple lithographs down here. We started out giving out the Monkey Head Nebula. We sold out of the Monkey Head. We had to go to the 30 Doradus, which is also known as the Tarantula Nebula. So if you didn't get monkeys, you got tarantulas, okay? And if you're afraid of spiders, well, I'm sorry, that's all we have left. Please come down and grab one if you didn't on the way in. Our talk, do I even need to say tonight, is, whoops, I got to turn this on. Our talk is Cassini's Grand Finale at Saturn. And we've been only waiting 19 years and 11 months for this because that's when Cassini launched 19 years and 11 months ago. Absolutely looking forward to it. It's a lot of fun. Upcoming next month, Elizabeth Tasker from the Japan Aerospace Exploration Agency. She'll be coming in and talking about dangerous worlds. Yes, exoplanets and such. All right. And you can see our familiar TBA coming in December and January, which means I was working on some stuff for the end of the fiscal year and didn't nag people to sign up for talks. Actually, I have one scheduled for January, but we may have to change that. I don't know, with the news. So, anyways.
It can still be on the 9th.
Yeah, okay.
As long as it's on the 9th, we can still
As long as it's on the 9th, great. We can do it on the 9th. Okay.
You'll get a tag team of people.
Okay. Ooh, tag team on the 9th. Okay. We still have some, there's a couple extra seats down here if the folks who are standing in the corner would like to. If you have a seat next to you, raise your hand so these guys don't have to stand for the whole night, okay? All right. Let's see, website. If you use your favorite search engine and look for Hubble Public Talks, you'll find this page with the list of the upcoming lectures, the links to watching it live online, as well as in the archive.